Hello everyone, I Dr. Megha Mishra welcome you all to the Swayam online course on first order logic in knowledge representation and reasoning. In the last lecture, you all have got the basic overview of the course. In our previous lecture, we have already discussed about knowledge agent, architecture of knowledge based agent, different levels of knowledge based agent and approaches to designing a knowledge based agent. Now, coming to today's lecture, in this we are going to learn about first order predicate logic, syntax and the basic elements of first order predicate logic. We will also discuss about the properties of quantifiers with examples. After that, we will go through the types of variables. In the study of propositional logic, we have explored representing statements using its rules. However, propositional logic is limited to expressing only factual information with binary truth values, true or false. It falls short when handling complex sentences as it cannot capture their intricate meaning and contextual interpretations. Propositional logic holds restricted expressive capabilities. For example, the sentences that cannot be adequately represented within its confines. Some humans are intelligent or Sachin likes cricket. To capture such statements, the limitations of propositional logic become evident. This prompts the need for more robust logical systems like first order logic, which can handle complex statements involving individuals, attributes and relationships. First order logic serve as an alternative approach for knowledge representation within the domain of artificial intelligence. It serves as an extension to propositional logic, offering enhanced capabilities. First order logic holds the necessary expressiveness to concisely capture the complexities of natural language statements. Also recognized as predicate logic or first order predicate logic. It stands as a potent linguistic tool for both conveying information about objects and establishing connections between these objects. First order logic is a more sophisticated logical framework that exceeds the constraints of propositional logic. In first order logic, the assumptions about the world go beyond just facts. It introduces the concepts of objects, relations and functions. Objects are the entities that populate our world. They can be concrete like people, numbers or colors, or abstract like theories or concepts. Relations in first order logic acknowledge that relationships between objects are a fundamental aspect of the world. These relationships can be unary, involving a single object, for example, red or round, or more complex, involving multiple objects like sister of has a color. Functions in first order logic serve as dynamic connectors. They relate one or more objects to another object or value. For instance, father of, third inning of and end of are examples of functions that can be linked objects or provide context to the relationships between them. By incorporating these elements, objects, relations and functions, first order logic mirrors the complexities of natural language more closely. It enables us to represent not only simple facts but also the intricate web of connections, attributes and interactions that define our understanding of the world. First order logic, like natural language, is composed of two fundamental components that govern its structure and meaning. Syntax refers to the set of rules that dictate how symbols and symbols combination can be structured to form valid expressions or sentences in a language. In the context of first order logic, syntax determines how symbols representing objects, relations, functions, logical connectives like and, or, not, and quantifiers like exist for all can be arranged to create meaningful expressions. It outlines the proper order, arrangement and usage of these symbols to construct well-formed statements within the language. Semantics, on the other hand, deals with the interpretation and meaning of these syntactic structures. It assigns meaning to the various symbols and combinations of symbols used in language. In the context of first order logic, semantics defines how the logical connectives, quantifiers, objects, relations and functions are interpreted, just as in natural languages where understanding a sentence requires not only knowing its grammatical structure, that is syntax, but also comprehending its intended meaning, that is semantics. First order logic relies on both syntax and semantics to ensure accurate and meaningful communication. By having well defined syntax and semantics, first order logic enables precise and rigorous representation of complex relationships and reasoning about various scenarios in a systematic and logical manner. The syntax of first order logic dictates the permissible arrangement of symbols to form meaningful logical expressions. FOL's fundamental syntactic components are symbols. In FOL, statements are often represented using concise notations. First order logic, that is FOL, is a formal system used in math, philosophy and computer science to express and reason about statements involving variables, constants, predicates, functions and quantifiers. It includes symbols for representing objects, properties, relations and operations. Quantifiers like for all and there exist allow statements about groups of objects. First order logic also uses logical connectives like and, or, not and implies to create complex expressions for precise reasoning. Atomic sentences serve as the fundamental building blocks of first order logic. They are constructed using predicate symbols followed by parentheses containing a sequence of terms. An atomic sentence can be represented as predicate. Inside the bracket we can write term 1, term 2 and so on till term n. For instance, the statement Ravi and Ajay are brothers can be represented as brother inside the parenthesis we can write Ravi comma Ajay. The statement Chinky is a cat can be represented as cat, inside the parenthesis we can write Chinky. So, in these examples brothers and cat are predicate symbols, while Ravi, Ajay and Chinky are terms representing specific individuals or objects. Atomic sentences allow us to encode simple relationships and properties in a structured way within first order logic. Complex sentences in first order logic are created by connecting atomic sentences using logical connectives. These connectives include and, or, not, implies and if and only if, permitting for more intricate expressions. First order logic statements consist of two key components: subject, the central element of the statement representing an individual or object, and second is predicate, a relation that connects two atomic sentences defining properties or conditions. By combining subjects, predicates and connectives, first order logic enables the formation of sophisticated statements to represent and reason about various relationships and conditions. For example, the statement x is an integer. It can be divided into two parts: subject. The subject of the statement is x, which represents an unspecified or general object, and second part is predicate. The predicate is an integer which describes a property or condition that the subject can possess. This breakdown demonstrates the structure of a basic statement in first order logic, where the subject and predicate work together to convey information about the properties or relationships involving the subject. A quantifier in logic is a language element that introduces quantification, specifying the quantity of objects within a defined universe of discourse. Quantifiers are symbols that help define the extent and scope of variables in logical expressions, permitting statements to refer to all or some objects within a specific context. The two main quantifiers are universal quantifier representing for all and the existential quantifier representing there exist. The two main types of quantifiers in first order logic. First is universal quantifier. This quantifier is associated with phrases like for all, everyone and everything. It asserts that a given statement holds true for every individual within the universe of discourse. Second is existential quantifier. This quantifier is related to phrases like for some and at least one. It states that there exists at least one individual within the universe of discourse for which the given statement is true. These quantifiers play a fundamental role in expressing different kinds of statements about the scope and range of variables within logical expressions. The universal quantifier is a fundamental concept in first order logic. It is a symbol used for logical representation to express that a given statement is true for every instance or object within a specific domain or universe of discourse. In other words, it asserts that a particular condition or property holds for every individual element being considered. The universal quantifier is represented by the symbol which resembles an inverted letter A. When we use the universal quantifier in a logical statement, we are essentially saying that the statement holds true for all members of a set. For example, consider the statement for all x where p of x implies q of x, where p of x and q of x are predicates. This can be read as for all x, if p of x is true, then q of x is true. This means that the implication holds for every individual x in the domain. It is also important to note that in the context of the universal quantifier, the implication symbol is commonly used. This implication symbol signifies that the truth of the antecedent. In essence, the universal quantifier allows us to make statements about an entire set or domain, asserting that a certain condition or property is universally true for all members within that set. If x is a variable, then the universal quantifier for all x can be read as for all x, for each x, for every x. For all x indicates that the statement holds true for every individual x in the domain. For each x signifies that the statement is true for each individual x in the universe of discourse, and for every x means that the statement is true for every instance of x within the specified context. All three phrases convey the same idea that the statement following the universal quantifier applies to every element or instance represented by the variable of x. In predicate logic, for example, the statement all men drink coffee can be represented using quantifiers and predicates. Let's break down the representation step by step. Variables and predicates. Let m of x be the predicate that represent x is a man, and c of x be the predicate that represent x drinks coffee. The statement all men drink coffee can be represented using a universal quantifier, and implication is for all x, m of x implies c of x. So, the breakdown of the representation will be for all x is universal quantifier, meaning for all x, and m of x implies c of x. This part asserts that if x is a man, m of x is true, then x drink coffee means c of x is also true. So, the complete representation in predicate logic is all men drink coffee can be represented as for all x, m of x implies c of x. This representation states that for every individual x, if x is a man means m of x is true, then it's implied that x drinks coffee, c of x is true. In other words, the statement asserts that every man is also a coffee drinker. Existential quantifier are a type of quantifier in first order logic that indicate that the statement within their scope is true for at least one instance of a certain condition or property. These quantifiers are represented by the logical operators which resembles an inverted letter E. When used with a predicate variable, it is referred to as an existential quantifier. In the context of the existential quantifier, the conjunction symbol or and is commonly employed to combine conditions. In short, existential quantifiers express the existence of at least one instance where a specific condition or property is true. If x is a variable, then the existential quantifier is represented as inverted e of x, and it can be read as there exists an x for some x for at least one x. All three of these phrases convey the idea that the statement following the existential quantifier holds true for at least one instance of the variable x within the defined context. For example, in first order logic, the statement some boys are intelligent can be represented using an existential quantifier and predicate. Let us break down it in variables and predicates. Let b of x be the predicate that represent x is a boy, and let I of x be the predicate that represent x is intelligent. So, the sentence or statement some boys are intelligent can be represented using an existential quantifier and conjunctions as there exists x such that b of x and I of x. So, the breakdown of the representation will be existential quantifier meaning there exists an x, and the remaining part which is b of x and I of x. This part asserts that there is an individual x who is both a boy, b of x is true, and intelligent, I of x is true. So, in first order logic, some boys are intelligent can be represented as there exists x such that b of x conjunction I of x. The statement is translated into first order logic as an existential quantifier with the conjunction of predicates. It asserts that there exists at least one individual who is both a boy and intelligent. This representation captures the idea that within a certain context there is at least one example of an intelligent boy. The key points and properties to remember regarding quantifiers are: the main connectives for the universal quantifier for all is implication. The main connectives for the existential quantifier there exist is conjunction, that is and. In the universal quantifier for all x for all y is similar to for all y for all x. In the existential quantifier there exists x, there exists y is similar to there exists y, there exists x. However, there exists x for all y is not similar to for all y there exists x. These properties help illustrate the behavior and relationships between different quantifiers and their combinations in logical expressions. They are important for correctly interpreting and manipulating statements involving quantifications. Now, we are talking some examples of statements and their conversion to first order logic. The first example is all birds fly. The predicate is here fly, inside the bracket or inside we can say bracket bird is used to represent the statement because all birds are implied to fly. The representation is for all x, bird of x implies fly of x. Second example is every man respect his parent. The predicate is respect x comma y. It is used to represent the relationship. The statement refers to the respect of each man for their parent. While we did not provide the complete representation, it could be something like for all x, man of x implies respect x, comma parent of x. Next example is some boys play cricket. The predicate is play x comma y, where x represents boys and y represents games, and we want to express that there are some boys who play cricket. The correct representation would be there exists x, boy of x and play x comma cricket. This translates to there exists at least one boy x such that x is a boy and x plays cricket. This correctly captures the idea that there are boys who play cricket. Next example is not all students like both mathematics and science. So, the predicate is like x comma y, where x represents students and y represents subjects, and the statement indicates that not all students like both mathematics and science. The correct representation should be not for all x, student x implies like x comma mathematics and like x comma science. This translates to it is not the case that for all student x, if x is a student, then x likes both mathematics and science. Again, some new examples of first order logic conversion are all cats are mammals. It can be represented as for all x, cat x implies mammal x. This states that for all x object, if x is cat, then x is a mammal. Some dogs are brown, represented as there exist x, dog x and brown x. This asserts that there exists an x object such that x is a dog and x is a brown. Every student has a favorite subject, can be represented as for all x there exists y, student x implies has favorite subject x comma y. This expresses that for all student x there exists a subject y such that x has y as their favorite subject. There exists a prime number that is greater than 10, represented as there exists x prime x and greater x comma 10. This states that there exists an x number which is both prime and greater than 10. Next example is no birds can swim. It can be represented as not there exists x, bird x and can swim x. This negates the existence of an x, that is bird, that can swim. In these logical representations, the relationships and conditions of the original statements are precisely captured using quantifiers, predicates and logical connectives. Next example is John loves Mary. John loves Mary, represented as loves John Mary. This indicates that John loves Mary. For every natural number there exists a larger even number. It can be represented as for all x there exists y, natural number x implies even number y and larger y comma x. This asserts that for every natural number x there exists a larger even number y. Some people are both doctors and musicians. Can be represented as there exists x, person of x and doctor of x and musician of x. This states that there exists a person x who is both a doctor and a musician. If a shape is a square, then it has 4 equal sides. It can be represented as for all x, square x implies has x comma slide and equal slide comma 4. This implies that for every shape x is a square and it has 4 equal sides. In these logical representations, the relationships, conditions and implications of the original statements are accurately captured using quantifiers, predicates and logical connectives. In the first order logic, quantifiers interact with variables in specific way. There are two types of variables, free variable and bound variable. Free variable is a variable that is considered a variable is considered a free variable in a formula if it appears outside the scope of any quantifier. In other words, it is not bound by a quantifier and can take on any value from the domain of discourse. For instance, in the formula for all x there exists y p x y z, where z is a free variable. Since it is not quantified, it can vary freely across the formula's instances. Free variable introduce a level of flexibility in formulas as they can assume different values depending on the context. Bound variable, a variable, is considered a bound variable if it appears within the scope of a quantifier. It is confined to the specific range determined by the quantifier. For example, in the formula for all x, a of x, comma b of y, both x and y are bound variables since they are within the scope of the quantifiers and represent specific instances within that scope. Bound variables are restricted to a particular quantified context and cannot be used outside of that context. They serve to specify the scope and applicability of quantified statements. So, in this class mainly we have discussed about the first order predicate logic, syntax and the basic elements of first order logic. We have also discussed about the properties of quantifiers with examples. After that, we have covered the types of variable, that is bound variable and free variables. So, in next lecture, we will cover well formed formula, that is WFF, which is a valid and syntactically correct expression in a formal language like propositional logic or first order logic. Inference rules and theorems proving provides a formal way to establish the validity of logical arguments. Forward chaining is a bottom up reasoning approach which we can start with the available facts or premises and use inference rules to derive new conclusions. Backward chaining is a top down reasoning approach where we start with a goal statement we want to prove and work backwards to find the premises that would make the goal true. With this, we will end our today's lecture here. Thank you for your patience and we will meet in next lecture. Thank you.